Aaron's main interests are in algorithms and machine learning, specifically in areas of privacy, fairness in machine learning, game theory, mechanism design, and learning theory. And we're very excited to have him talk about human-AI collaboration today. Thank you.
Thanks very much, and thanks to the organizers for having me. This is going to be a very different kind of talk, but hopefully still interesting. And this is joint work with a bunch of great collaborators, many of whom are my students and colleagues at Penn, and with Emily Ryu, who was a PhD student at Cornell, advised by Ava and John Kleinberg. We did this work over the summer when she was visiting us. Emily tragically died in the fall. She was a really bright light and really enjoyed research and this research, and I hope that some of that joy comes through in the presentation. And there's no good transition from that to slides. Okay. So what I want to talk about is how maybe a person and a machine who have different views of the same thing, and therefore might initially have different predictions, different suggestions for what the right course of action is, can nevertheless work together to to make better choices in the real world. I did not know that today was going to focus on applications to medicine. I do not want to pretend that I know anything about medicine. This is a cartoon example in the style of theoretical computer science. But I will use a doctor as my cartoon analogy in the talk. And there are two aspects that I hope to talk about, although it's OK if we get lots of questions and we only talk about the first one. I want to talk about first complementarity and agreement. Suppose we've got two parties that have different views of the same thing. This is very natural if the two parties are, for example, a person and a machine learning model. They might very well disagree about what the right thing to do is, have different estimates for all sorts of quantities. Is there a natural way for them to interact to come to agreement in a way that is accuracy improving in various ways? That's the first thing. And the second thing is, are these methods for coming to agreement robust to the situation in which the two parties might actually have different incentives? Suppose the companies that are deploying language models, for example, don't want exactly the same things as their users. How should we think about that? Is that an insurmountable problem when it comes to collaboration, or are there things we can say? OK, so let's start with the first problem. And just to set up the cartoon example, imagine a sort of predictive medicine tool used in some diagnostic application. And what happens is patients arrive, and they've got observable features. And some of those features are legible to both parties, say the doctor and the machine learning model. But there's other features that are potentially only legible to one of the parties. So for example, the doctor might, since she's got the patient in front of her, have the ability to make essentially qualitative observations that are difficult to encode in a way that's legible to the machine, but are nevertheless diagnostically relevant. Okay, there's sort of things about patient disposition that are hard to sort of encode in a CSV. The doctor has extra senses, smell. There's all sorts of stuff that might be diagnostically relevant, but is hard to encode, to ChatGPT, for example. On the other hand, these models are pretty good at what they do, and might be better at interpreting all sorts of things than doctors are. They've seen a very large amount of training data. They might be better at analyzing numerical patterns in various ways. And so we shouldn't discount that maybe even today's models, but certainly future models, might have things to add beyond the doctor's informed opinion, based on observations that are not easily legible to the doctor. And so, OK, we've got sort of two parties that have potentially fundamentally different views about the patient in front of them. The machine might make some prediction, either about some event or maybe a course of action, what's the right treatment. And even if we're in some future scenario where the machine is very good, because the doctor just has information the machine does not, we might find ourselves in a situation in which the doctor just fundamentally doesn't agree with the model and perhaps ought not to, because she knows stuff that the model doesn't. Okay? And so the question is, what should she do at this point? I mean, she could just make like a snap judgment and say, I think this is one of these special cases where I know something the model doesn't, and I'm just going to discount the model's recommendation. But it would be better, perhaps, if there was some way for her to interact with the model that would combine the sort of useful pieces of information that both parties have in a way that leads to more accurate predictions and hopefully better treatments, right? Rather than simply disregarding sort of the predictions of a model that you think are wrong, like the whole premise perhaps is that the model has information that might also be diagnostically relevant that you do not. It has a different piece of information. That's why you disagree. Maybe there's a better way to combine information that leads to better decision making. Okay, so that's sort of the question that we want to study, like how should we do this? And because these different pieces of information are mutually illegible, the answer is not just share all of the information and come to the optimal decision for various reasons. But in particular, you can't just, you can't encode smells for GPT-5, and you're not going to read through all of its training data. Okay. So, having heard this story, if you happen to have been educated in economic theory and statistics rather than medicine, this might remind you of a classical theorem called Aumann's agreement theorem in a very stylized setting. So has nothing to do with, how you would, we'll get to how it might apply to this scenario a little bit more closely, but let me tell you what Aumann's agreement theorem says. It says that if we've got two Bayesians, okay, like a Bayesian is someone who knows really a lot about the world. They have a correct prior overall, over the joint distribution of observable features of the patients and, what their correct diagnoses are. They're able to correctly condition on their observations, whatever those observations are, and form a posterior. Okay, Bayesians don't really exist, but suppose you did have two of them. And not only did they have the same prior, but they had common knowledge of each other's posterior belief. What does common knowledge mean? Common knowledge means not just that I know what your belief is, and you know what my belief is, but I know that you know what my belief is, and you know that I know what your belief is, and so on and so forth ad infinitum. Okay? Then we have to have the same beliefs. The sort of tagline that goes with this theorem is often that Bayesians cannot agree to disagree. Okay, initially the two parties, since they have different observations, might have different beliefs. But if I know your beliefs, that tells me something about, like what you saw, and I can update on that. And if you know my beliefs, then okay, ad infinitum, this converges to the same posterior. That's Aumann's agreement there. Okay, now ad infinitum is a long time. It's been known for quite a while that you don't actually need common knowledge, which is sort of the infinite regress of a conversation about our beliefs. If I tell you my belief and you update, and then you tell me your new belief and I update, and we go back and forth, this will converge after a finite number of rounds. Finite numbers can still be big. In 2005, Scott Aronson showed that at least if we're talking about one-dimensional things, like the probability of some binary outcome, for example, then we don't need an infinite number of rounds. That's right, we don't even need a enormous number of rounds. If we're happy with epsilon agreement, which means that if my estimate of the probability of some event is within plus or minus epsilon of yours, we won't quibble anymore. We'll shake hands and we'll call it a day. Then we only need on the order of 1 over epsilon squared rounds of conversation before we get epsilon agreement. So this is pretty interesting because it's independent of the complexity of the instance, right? Like the real world's probably pretty complicated. You've got high-dimensional, covariates describing these patients. The relationship between those covariates and the outcome could be really complicated. What this is saying is none of that matters. Like the rate of agreement depends only on the quantitative degree to which we, are happy to say we agree. It doesn't depend on the complexity of the world. So that's pretty good. Okay. So this is, the story through 2005. Now, you might think, okay, well, the problem with our, model of the doctor and the machine learning model is because these observations are mutually illegible to one another, they can't share them. Maybe this kind of thing solves that problem because nowhere here do they need to share their observations. They only need to share their beliefs. Right? But like, nevertheless, there's, if you think about it even a little bit, quite a few drawbacks to the story that I've told. Basically, you can object to every part of it. Okay, so first of all, like, in order for this story to make sense, first you need to believe that there is a distribution from which patients, and their covariates and maladies are sampled IID. Like, you might not believe that. Even if you do believe that that's a reasonable modeling choice, you need to believe that we know the prior. In fact, both of us know the prior, both parties, and they agree on it, right? Knowing the prior is a big problem here, right? If the covariates are complicated and high-dimensional, the world is a complicated place. The correlations between those covariates and the outcomes are complicated. Why do we know the prior? Why do we agree on it? Even if we did know that, performing Bayesian updates is computationally intractable. Even just figuring out what the posterior is given the thing we directly saw about the patient, let alone the thing we need to do to make the story make sense, which is update my beliefs conditional on your stated beliefs, which involves integrating over all of the possible things you might have seen that would have led to the prefix of conversation we've seen so far. So even if we did have a prior, this is very far from something that you're actually able to do. We definitely don't want to assume it of the person, and like, if you are the developer building this model, and this is the model of the world we're relying on, you're on the hook for implementing it, and that's also going to be a problem. This finite convergence, this fast convergence theorem is about one-dimensional expectations. What's the probability of something? But of course, there might be like 1,000 diagnostic codes at your hospital, and you don't want to, like, the beliefs are somehow over some distribution over those diagnostic codes. It's not clear how this story would generalize to sort of a more realistic setting. So these are all sort of objections to like this classical kind of model. And so what we want to ask is, can we relax all of these unrealistic behavioral assumptions to get something that is, at least computationally and statistically tractable, something that in principle you could implement that will lead to the same conclusions. And when I say relax, I don't mean like design something like totally different. I mean like specify properties that a Bayesian would satisfy. So like if you believed in a world of Bayesians, like you would also be happy with the properties we write down. We want to write down something strictly weaker so that we don't want to rule out that someone is, we don't want our thing to, we don't want our statements to not apply if someone's too smart and they're actually able to make correct inferences. But we want to assume much less of them. That's the goal here. And the answer is going to be yes, we're going to be able to sort of do away with all of the sort of distributional and Bayesian machinery. We're going to be able to make statements only with sort of frequentist quantities that we can measure and enforce tractably. Okay, so quick overview of what we're going to do. So we're going to move to a totally like frequentist setting where you don't need to believe in distributions. You certainly don't need to know those distributions. We're going to think about settings. Oh, yes.
Quick question. The updates are based off of the knowledge that they have about the other Bayesian?
In the Bayesian story, yes.
Okay.
Like I know that you're a Bayesian, and so when you tell me your belief, I can, and because I know the prior, I can integrate over all of the observations you could have made that would cause you, so it would be complicated.
And then that's responsible for your updated belief that then I process.
Exactly, and in general, you would be integrating over all observations I could have made that would have led to the whole transcript of conversation we've had so far. So it's all, something that like notationally makes sense in a Bayesian model, but is, gets increasingly implausible.
Yeah, makes sense.
Okay, so we don't want to do that. We want to move away from that. We want to base the whole thing in an entirely sort of frequentist model with things we can just like measure from transcripts and tractably enforce with algorithms. What we're going to be able to do is we're going to be able to recover and generalize these theorems even at the same quantitative rates, essentially using sort of refinements of calibration, which I'll talk about a little bit. And of course, agreement on its own is not necessarily what you want. If I just said I want a model that can interact with a human being and quickly come to agreement, I could do that with like a print statement. Whatever the person says, shakes hands and says like, sounds good to me, I agree. In order for like these kinds of agreement things to be interesting, they need to be accuracy improving. And so one thing you can do here is you can give theorems that sort of say, okay, well, the prediction you come up with or the action you take is going to be competitive with the best thing you could have done in some class that had access to the joint features of the person and the machine, even though those features were never shared, can't have been shared because they were mutually illegible. Okay. Oh, yes.
Is there still a prior here, a common prior?
I'll tell you the model, but no. Like I'm gonna tell you results. So, okay, the result I will tell you about is a purely frequentist, worst case online learning kind of thing, no distributional assumptions at all. But all of the conditions I'm going to ask for, because they would be satisfied by a Bayesian if there were a prior, all of our theory, and I won't have time to tell you about this, but if you believe that there is a prior and examples are drawn IID from this prior and people know it and update, all of our theorems, even though they're proved in this frequentist world, lift back up to the Bayesian world. And so the generalizations we get of Aronson's result, which is for Bayesians, we're going to generalize this to high-dimensional settings where people are talking about treatments rather than beliefs. We will recover, as a corollary, theorems of that form for Bayesians, even though the theorem I will tell you about natively lives in a worst-case frequentist setting.
When you recover the Bayesian results, then it's still a common prior between the two parties.
The Bayesian results are a world in which there's a common prior and people are doing Bayes updates. The core theorem we have has nothing to do with that, except that the conditions we assume are weaker than you would get from a Bayesian world. Okay. So let me tell you quickly about calibration. So probabilities are tricky things if you think about them. What does it mean when someone forecasts a 70% chance of rain? Does it really mean that it's going to does it mean that there's real stochasticity in the universe? I forecast a 70% chance of rain, and God is going to flip coins, and there's really some sense in which starting now the universe is sampling from a Bernoulli distribution with probability 70%. I mean, maybe, or maybe if we took more measurements and recruited enough twins and did the right study, then it would be possible to make these predictions with zero error. Maybe everything's deterministic starting from now. It's just fundamentally impossible to distinguish a universe in which everything is deterministically encoded in the low order bits of background radiation or something, if only we knew how to access it in a world in which there's true stochasticity. So that's not a question you can hope to address. Okay, so what do you do? Someone tells you that they think there's a 70% chance of rain tomorrow. It's very hard to evaluate that statement in isolation. But weather forecasters typically don't do that. They're employed as weather forecasters. They're not just sort of one-off weather forecasters. They make predictions every single day. And when you have data like that, you can start subjecting it to sort of sanity checks. Again, you can't tell whether these are sort of fundamentally true probabilities or not, because for all you know, the universe is deterministic, if only you learned the right secret. But real probabilities would satisfy certain properties, and you can test whether this sequence of forecasts satisfies some of those properties. So for example, if these were real probabilities, then if I looked at all of the days for which the forecaster predicted a 70% chance of rain, and I thought, okay, well, God is flipping coins. We've got samples from a Bernoulli distribution where p is 0.7. One property we would have is that in the long run, at least, it would rain about 70% of the time. Okay, the prediction would be unbiased, conditional on the prediction itself. Okay, and this forecaster passes that test. It wouldn't just be the case for 70%, it would be the case for everything they predicted. If I looked at the days for which they predicted a 20% chance of rain, and there were enough of those, it would rain about 20% of the time. Okay, the forecaster fails the test here. So you can be calibrated without making sort of without forecasting real probabilities, whatever that means. But real probabilities, if you believe they exist, would in the long run be calibrated. And calibration's a purely frequentist property. Like if you have enough data, you can just test how calibrated you are and see if that's like further than you would expect to be in a model of the world where people were forecasting real probabilities. Okay. So let me tell you now about like the frequentist setting I want to think about. So I want to dispense entirely with priors and a Bayesian model. As a result, we're going to need to talk about more than one patient. For the same reason that it's hard to evaluate a weather forecast in isolation when someone says there's a 70% chance of rain tomorrow, but that's the only forecast they're ever going to make. It's going to be hard to do anything without sort of strong distributional assumptions if there's only ever one patient. But we can start to do things in a sequential model where a doctor, isn't just a one-off hobbyist, but like treats patients routinely. And so in our model, time will proceed in rounds, t. And every day, a new patient will arrive. And this patient will have features that are legible to the human and features that are legible to the machine. They don't have to be disjoint. There might be all sorts of stuff that's legible to both. But like there might be stuff that's legible only to one or the other. We make no assumptions about where this patient comes from or where these covariates or eventually the label come from. They're not assumed to be drawn from a distribution. If you're a computer scientist, we're going to be working in what's called an online adversarial model. So we want guarantees that hold for any sequence, not because we believe the world is necessarily adversarial, but because we don't necessarily understand what the world looks like and how things change. And if we can get results in a robust model like that, then maybe we don't have to worry as much about the assumptions that we made, like not holding at deployment time. Okay, so this patient shows up. And I'll talk a little bit at the end about having these conversations about actions, but I think this discussion will be a little bit easier if we just talk about like one-dimensional probabilities. So let's say we're trying to predict, the probability of some event. Okay, so the doctor maybe like goes first and says, you know what, like given what I see and like my medical training, I think the risk is 0.2. And feeds this to the machine. Machine does something, might take this into account as well as the observations it has made and says, I disagree. I think the risk is something else, 0.4. Human thinks about this, takes it into account somehow. We're not assuming they're doing Bayes updates. There's not even a distribution. They're just doing something. And they say something else. So I think it's 0.34. And the machine says something 0.32. And you know what? Like maybe that's close enough. If epsilon's 0.02, we'll shake hands at this point and say we agree. At which point the label's observed. And then the next round occurs. Another patient walks into the door. Again, no distribution. This patient might not have anything to do with the prior one. They too have features that are legible to the person and the machine. And another one of these conversations transpires. And hopefully at some point, maybe at a different round, it ends in agreement. Another patient comes in, okay, so on and so forth. Okay, so every, let's say, day, a new patient arrives, and the conversation takes place in rounds. We can think about the sequence of predictions the person made at round 1 or round 2 or round 3. Does the picture make sense? Okay. If like sort of the Bayesian setting would correspond more to these patients being drawn IID from some distribution that both parties know, that could be what's happening, but is not something we're assuming. Ooh, a lot of questions there. We hope to prove that there are conditions that will cause that to happen, but it's not assumed.
It seems like a sort of restricted form of communication. Like
your conversations are more interesting than this?
Yeah. Is it like surprisingly rich, or?
We are going to show that good things can happen with this form of communication, but I agree with you that I would hope that the conversations that my doctor is having are richer than this. But like you can already get pretty good things here. But if I were advising someone designing a predictive medicine LLM, I would not suggest that they stick to this.
Are you making any assumptions about what the doctor is willing to believe or attribute to the machine?
The only sort of assumption I will make about what this, the properties of this conversation, I will tell you on the next slide, and the theorems will follow from sort of that assumption. Otherwise, this can be anything.
So in this more simple model, is the updating only based on your counterparty's replied risk score? Or?
You know, again, other than the structural property I'm going to want to impose on the next slide, anything can be happening. But like the things that you've observed at the time that you make your prediction are the features that are legible to you, the prefix of conversation that has happened so far, and the conversations that have happened about patients on previous days and the outcomes. And the algorithm can, in principle, make predictions as some arbitrary function of all of that stuff. Now, obviously, not all algorithms will have good properties, and I'll say I'll enunciate a condition that an algorithm might satisfy that would cause good stuff to happen. Any other questions? Okay. Good. So let me tell you like what this condition is that, you know, if it happens to be satisfied, good stuff will happen. We call it conversation calibration. So it's going to be a refinement of calibration. It'll be a somewhat stronger condition than calibrations I told you about, but not much stronger, in that it's still going to be easy to measure from not much data, and maybe more importantly, there are algorithms that will guarantee that your predictions have this property, even in the worst case, in like an adversarial sequence. You can guarantee this thing that we're going to call conversation calibration without making any distributional assumptions. These are just frequentist kinds of statements. Okay. So what is conversation calibration? It says the following. Let's look at a particular round, like round 2 of conversation. Okay, so say maybe it's the machine speaking at round 2. Okay, there's a sequence of predictions that they made across time in round 2 of the conversation. Okay, in general, by the way, like since the conversations end at different times, like the sequence of predictions made at some round might not be of length, you know, capital T, but like take all of the rounds that made it to take all of the rounds that, all of the days that made it to that round of conversation, you have some sequence of predictions. Okay, look at that sequence. Now, looking at this sequence of predictions that the person made at round 2, look at what their counterparty, in this case the machine, predicted at the previous round, in this case round 1. Okay, and let's restrict attention to days in which their counterparty predicted something, like 0.1. Okay, in fact, in order for this to be, in order for this to really make sense, you have to restrict to days in which they predicted roughly 0.1 plus or minus something, just so it's not like only a single day. Okay, and so we are going to like restrict attention to what the counterparty predicted at the previous round, not on all previous rounds. We don't want to condition on the whole conversation so far, which is what a Bayesian would do. Okay, that would quickly lead to like 0 samples. Like it's very unlikely that for a conversation of length 100, I've ever seen a patient who caused that exact same conversation to happen. A Bayesian would condition on all of that, but that's too hard. We're going to condition just on what was said by the counterparty at some previous round. Okay. For a particular value, like 0.1, that will subselect a set of predictions that we made at round 2. Okay, so we're looking at the sequence of predictions at round 2 in this case, and we're subselecting a particular subset of rounds that are defined by their counterparty making a particular prediction at the previous round. Conversation calibration just asks that this sequence of predictions be calibrated to the outcomes. Okay, and similarly for every round and every value of the prediction that your counterparty might have made at the one round previous, we want that sequence of predictions to be calibrated to the outcomes. So we're asking that every round of prediction is calibrated to the outcome, not just marginally, but like conditionally on the value of what your counterparty predicted at the previous round. Not, importantly, not conditional on the whole transcript so far, which is what a Bayesian would do, just conditional on one round previous. Yeah?
And so if I think about day 0, you're requiring everyone to be calibrated?
That's right. So in particular, like, we want that the predictions should be calibrated, and more than that, we want them to be calibrated, like, conditional on the previous prediction, if there was such a thing. Okay? And this is because we're only conditioning on a modest number of events, just sort of what was said yesterday, one round previous, not all rounds previous. There are efficient algorithms that will guarantee this, even in the worst case. Okay. Okay. So what we can show, and this is, I have only talked about like perfect calibration, like calibration has, like you can't get perfect calibration. There's like some approximation parameters that I haven't told you about. So don't try to like read the slide. But the theorem that results is that, if the calibration error is sufficiently small, and there are algorithms that will guarantee this with, t, the total number of days, being only modestly large, then you recover sort of quantitatively the sort of Scott-Aronson variant of the agreement theorem with the same parameters that to reach epsilon agreement, you only need 1 over epsilon squared rounds of conversation. Okay, so you can recover this theorem, and because Bayesians would be calibrated, they would be using what are in the model real probabilities, and they would satisfy calibration conditional on everything, and in particular conversation calibration. It's not too hard to like lift this theorem to recover the existing Aumann's agreement theorem. Yeah.
When are the outcomes observable to the agents?
We assume that the outcomes are observable after the conversation for every patient. So it's not a partial observability model.
Okay, so at the end of every day? Or
At the end of every day, that's right.
Like before the next conversation.
Before the next conversation, that's right. And you could imagine variants of this that had delayed feedback and bandit models, and you could do stuff, but we haven't. Okay. Now, once you have this like machinery, yes.
I had a question on that. Is there anything about this that's a human and a model? Like, could this be a model and a human and a human?
Absolutely, yeah. So I mean, like, because I don't really know what AI is, but yeah, there's nothing here that is like specific to a human and a model. This could be, like it's saying conversations that satisfy this conversation calibration property will lead to accuracy improving agreement. Part of the, and because it is most interesting when something when it's not in the solution space to just like jointly learn on your to sort of learn on your joint observations, because that's something you could do. And so I think for a human and a model, there's a nice motivating story for why you can't do that. The observations might be mutually illegible, but yes, like this is, okay. So like, once you have this machinery to sort of think about agreement from calibration conditions, you can generalize it. So there are fancier notions of calibration. So we sort of talked about predicting, like a one-dimensional, probability. Now, what if there's, like 1,000 diagnostic codes in the hospital? Like, first of all, like you'd need like another agreement theorem, and also like, it was already objected to that these conversations were like a little boring. Like if the object of interest was a distribution over 1,000 things, every round of conversation would involve enunciating a 1,000-dimensional vector. It would be hard to do. You'd expect that agreement would take a really long time. Now, there might be like 1,000 diagnostic codes at the hospital, but probably there's only, like a handful of things that the doctor might reasonably like suggest. Like, there's not a unique treatment for every diagnostic code. Many things are, take 2 Tylenol and call me in the morning, even though like the specifics of what particular virus you have, might differ between cases. And so, what you can do is you can rig things up with similar machinery so that the conversation can happen can talk only about actions, only about, say, treatment options. We don't have to report like full belief distributions. We can sort of say, I think that given my unenunciated, like internal beliefs about the distribution over diagnostic codes, like what we should do is amputate the left arm. And you can say, no, I think we should amputate the right arm. And finally we agree on prescribing ibuprofen. You can write down a very similar model where you just talk about actions and quickly lead to accuracy improving agreement, where accuracy means, in this case, improving the utility of your actions at each round. OK. So I only have 5 minutes, so let me just very, very quickly skim over this second collection of results. The protocols I've described so far assume that both parties have the same goals. They're both trying to estimate the probability correctly or choose the sort of utility maximizing action for the patient. They agree on the utility functions. But you might worry that like if the LLM has been produced by some corporate entity that doesn't agree with you about what is the right thing to do in the world, that they might, for example, try to steer the conversation to get you to agree to something that is not like actually what is in your best interest. And so, for example, I don't know, just to continue the toy, suppose the AI model in this predictive medicine application was built by Johnson & Johnson. Like maybe it's got a similar utility function to you in some cases, like it sort of thinks you should correctly diagnose patients and treat them, but like on the margin, it kind of prefers that you prescribe Johnson & Johnson drugs over other prescribers. And so maybe the model, tries to like steer the doctor in this direction, gets them to agree, but like actually like that's not what like an aligned model would have done if the model was pulling in the same direction as the doctor. And so the thing we think about in the second part is, like, fine, that's a problem. But what if the Johnson & Johnson LLM is not the only LLM on the market? What if there's actually a market of LLMs out there that you can choose, and you can choose amongst them. You can choose which one to interact with. So maybe there's like a Pfizer LLM as well. That one's not aligned either. It's sort of just as misaligned as the Johnson & Johnson LLM, but in a different way. It wants to prescribe Pfizer drugs. Is there a chance that competitive pressures in the market for LLMs can result in sort of the human having sort of as good sort of decision-making power as they would have had there been a perfectly aligned LLM? OK, so I'll skip through the formal details of the model, but the idea is, what's a model here? It's just like the weights of the LLM. Think of it as a conversation rule that maps, the features it sees about the patients and the conversation it's had so far to like the thing it says next. The models are deployed. The doctor can sort of play around with them and experiment and figure out which one is best for her own use cases. Then she'll she'll sign a contract with whichever provider seems to be most useful to her, and then she'll just treat her patients with that one. OK? There's some formal model, but you get it. OK. So this is there's some strategic interaction now between the LLM providers. Oh, and one important thing is, in the model here, it's not that the LLM providers like the thing they care about, it might be misaligned with the doctor, but the thing they care about are the actions the doctor takes. It's not like they want to be chosen for its own sake. Like they want the doctor to prescribe Johnson & Johnson drugs, for example. OK. And so now that there's multiple LLM providers that the doctor can choose amongst, there's like a strategic game between the LLM providers. They can choose which LLMs to deploy. Then the doctor will choose one to interact with, and that will result in some sequence of actions that they have preference over. But like if I'm the Pfizer LLM, I can't just, or if I'm Pfizer, I don't want to deploy an LLM that just says, for every patient, prescribe Viagra, even though that would be a great outcome for me because the doctor won't choose me. OK. So, like the best case for the doctor is if the LLM provider was perfectly aligned with them. They were deploying an LLM purely to maximize the doctor's utility. OK. Let's call the payoff the doctor would get in that amazing world opt. They're not going to get that. Maybe they're not going to get that because the LLM providers have different utilities. But the thing the thing we do show, but I can't tell you about in very much detail, is that if the market for LLM providers satisfies a much weaker condition called market alignment that does not require that any of the LLM providers are aligned, then the human doctor can get utility opt in all of the Nash equilibria of this game. And very roughly speaking, market alignment means, if you like plot out what the LLM provider's utility functions are and what the doctor's utility function is, even though the doctor's utility function might not be equal to any of the LLM utility functions, it's in the convex hull. More generally, can be written as some non-negative linear combination of the doctor's utility functions. If that is indeed the case, and the Johnson and Pfizer example is an example of this, right? Like, the misalignment of the Johnson and Johnson LLM and the Pfizer LLM are kind of in opposite directions. The Johnson & Johnson LLM is misaligned with the doctor in that it wants to push Johnson & Johnson drugs. The Pfizer LLM is misaligned with the doctor in that it wants to provide Pfizer drugs. These directions of misalignment kind of cancel out, and the doctor cares about something in the convex hull. And this is the generalization. Okay. If you live in a world in which you have market alignment, even if you do not have individual alignment with any of the LLM providers, in all Nash equilibria of the induced game, like, the doctor gets the utility she would have gotten even if you had perfect alignment. Okay.
So if it's not, would it not be a market equilibrium if, for example, the generic drug, which is in no one's incentive to prescribe, is actually optimal?
Yeah, let's see. So generalizing the story might require an LLM provider that was associated with like every drug manufacturer.
Or like maybe J&J has like the expensive thing, the cheap thing. They never want you to do the cheap thing.
If there's something that all of the sort of AI providers don't want, but the doctor wants it, then you're not going to satisfy this condition. And if you think about it for a bit, like, there's nothing you can do. Nobody's going to give you the information you need to push in that direction. Okay. Yeah, so all done. Just to summarize. Okay, closing thoughts. Like, real probabilities are like super useful. Like, you can do all sorts of stuff if you knew truly like the probability of outcomes given everything you had observed. Like, you can make Bayes optimal predictions. You get these like agreement theorems. But like, even if you make philosophical commitments that like posit that these things exist, and like you might not, like in general, you just can't get your hands on them. Real probabilities are too hard. But what are real probabilities? Like, one way to think about them is they're numbers that happen to be unbiased estimators for the outcome, not just marginally, but conditionally on anything you could possibly have observed. It's the anything you could possibly observe that makes them hard. Calibration is like calibration conditions are much weaker conditions that only ask that your predictions are unbiased, subject to like a small number of things. And it turns out that there are algorithms that can guarantee various kinds of calibration so long as the number of things you're conditioning on isn't too big. And oftentimes, if you look at what you're actually using the probabilities for, you didn't need that they were real probabilities in their entirety. You didn't need that they were unbiased conditional on everything. You only needed they were unbiased conditional on the stuff that was relevant for your task. And sometimes that's not that much stuff. So, in this case, we recovered things like Aumann's agreement theorem with a collection of much weaker conditions. There's like a whole bunch of other stuff you can do that real probabilities are useful for, but it turns out you only need a tractable subset of the bias conditions. Yeah, and that's it. Thank you.
Thank you so much. We have time for maybe one or two questions. Just, yeah.
Hi. So for the first part, like, given that it's unclear that humans would run like online learning algorithms that are conversation calibrated, I guess I'm wondering whether your theoretical result like gives some kind of practical insight that you.
Yeah, great.
For doctors that are actually, interacting with.
Great question. I have only unsatisfying answers, but like, okay, so we give some condition under which good things happen, and it's totally sensible to ask, like, maybe that condition's not satisfied. A couple of things I would say. So first of all, this is only like a weaker condition, a substantially weaker condition than sort of Bayes rationality. So to the extent that we're sort of starting with some set of results that would be nice to have, but live in an overly idealized world, we're sort of working on weakening what we assume and trying to get to the same place. The other thing is, because these are conditions for which there are simple algorithms that can tractably guarantee them, at least on the model side, we can guarantee it. And the kind of thing you could provide to a doctor, although there's reasons why this would be unsatisfactory in various ways, but you could provide a way, I think of it as like a megaphone they could speak into. They would speak in sort of arbitrary probabilities. What would come out would be appropriately conversation calibrated probabilities. And the thing we could promise about them is that the mean squared error of the things that came out of the megaphone was smaller than the mean squared error of the thing that went in. So like, you can promise these things in accuracy improving ways. Now, of course, this would lead to agreement with the megaphone, not with the doctor. And so excellent question. There's things to say about it. They're not completely satisfying. But I'd say the main thing is that these are substantially weaker conditions than you might have had to assume previously.
So I think, should we take the questions offline? Because so as to make sure we leave time for coffee. Yeah, so thank you so much, Aaron. Okay.
Thank you.
Yeah, and we'll be back at 11.